Hello physics students. So in the last few videos, you learned how inductors affect electric circuits. Inductors act like inertia, but for current. And what that means is that when you turn a circuit on, rather than the current jumping almost instantaneously up to its value and then continuing on at a constant value, what happens is the current gradually increases up to that value. Or in a circuit with current in it, when you try and shut it off, what will happen is rather than the current dropping nearly instantaneously to zero and then being zero with time, it gradually decays down to zero. So an inductor is like inertia, it's like mass in mechanics. What it does is it tries to keep the current at a constant value. And the way it does that is by creating a voltage through Faraday's law, induction, because it's a coil, and when you try and change the current, you're trying to change the magnetic field, you're trying to change the magnetic flux, which creates a voltage in the opposite direction of the change, which means there's a voltage keeping the current going when you're trying to drop it, or opposing it when you're trying to drive the current forward. So in this video, what we're going to do is see how that device, that inertia, electrical inertia, influences a circuit that has a capacitor in it. We're going to look at the simplest kind of circuit, just an inductor capacitor circuit, an LC circuit. So what I have here is one circuit diagrammed at 4 different times. Imagine I start this circuit with a fully charged capacitor at plus Q0. What I'm basically specifying is the charge on the top plate. Of course, the capacitor is totally uncharged because it has a net zero charge, but we're talking about the top plate. We got an open switch and an inductor, so there's no current, only charge. So then I flip this switch down. What's going to happen is the current's obviously going to want to go in the clockwise direction so the plates and the capacitor get neutralized. And that eventually happens. Really, it's the electrons flowing the opposite way to the positive plate, and at some point, the inductor becomes fully uncharged, but there's current in the inductor. And remember, an inductor is like inertia. So while that current built up, the inductor now keeps the current going. And that drives the capacitor to become charged in the opposite polarity compared to the original. So now we got a fully charged capacitor again. The charge on the top plate is minus Q0, the opposite of the original. So again, the current wants to now go this way. In other words, the electrons want to go in the clockwise direction, current in the counterclockwise, so the capacitor can become neutral again. So that happens. The current goes through the inductor, and eventually the capacitor plates are neutral again. But again, we have current now in the inductor. And the inductor doesn't let it just drop to zero. It's an inertia. It keeps that current going. And so now this plate continues to get positive, and we get back to the original. And that repeats over and over again. So that's what an inductor does. It creates almost like simple harmonic motion in mechanics. So let me create a pause to give you a chance to copy these diagrams down to the best of your ability. All right, from here, it's a little unclear where I need to go with this video because the curriculum published by the College Board says one thing, and then the videos they put out say another. And in the curriculum, it says nothing about creating differential equations for these circuits and solving for the current as a function of time. But in their videos, they show that happening. So I'm going to include this, but this part is technically, according to the published documents, not part of the curriculum. I'm going to include it anyway, just to sort of cover our bases here. So if you wanted to derive the expression for the current as a function of time, and the charge as a function of time, and possibly even the period of oscillation as this is going around and around, how long does it take to go around in one cycle? Then you would do this. You would write a differential equation, which, as I've said all throughout this course, with circuits, the way you create a differential equation is you use Kirchhoff's loop rule. You imagine you're a little tiny ant with a little tiny voltmeter, and you're going to go around this circuit and measuring the voltages as it's evolving in time. So when our little ant walks from the negative plate to the positive plate of the capacitor, it's going up in volts. How many volts does it go up? Well, remember, C equals Q over V. So if I solve for V, it's Q over C, and plus because we're going up. And then we go through the inductor, and the voltage in an inductor is negative LdI dt. We learned about that. Oh, by the way, this question mark is here again because I don't know if this is technically part of the curriculum. It might just be excess knowledge for the AP, but that's okay. So now what I have to do is solve this differential equation. The problem is I got two different variables, charge and current. So what I'm going to do, and notice I color coordinated here, I'm going to replace I with the derivative of charge with respect to time. Now, why did I put a minus sign? Because this capacitor is discharging in the beginning. So dq dt is technically negative when the charge is going down. But I want current to be a positive value. I'm going to define this as positive current. So if dq dt is negative, let me add an extra minus sign so I have negative, negative, and then this whole thing is positive. So now this technically is charge here and double derivative of charge. The way we solve this is we realize that this is the differential equation of an oscillating system, or we could just know it from the physics behind it. And we pick a solution for charge that oscillates the cosine function. Why did I pick the cosine, not the sine? Because I know the charge in the beginning is beginning at plus Q0. I want the charge to begin at non-zero. That's the cosine function. Technically, you could put a phase angle in here to make it the system start at any point you want. But I'm just going to leave it here. So I plug this Q into these two places, take the derivative twice, cancel all the terms that I can. For example, if I take the derivative twice, I get negative omega times negative sine. Take the derivative again, I get now negative omega squared times cosine again. So I've got cosine in both terms. The cosines can go away. The Q's can go away. I'm not going to go through all those details because, again, I don't know if this is even part of the curriculum. But you would go through, take those derivatives, cancel all the terms, and you'd eventually get to omega squared equaling 1 over LC from this analysis. And we remember, how does the omega function work? Omega is 2 pi over the period. And what that means is that every time little t goes from 0 to capital T, we have another 2 pi in the cosine function. It's gone through its cycle. So it's just, just thinking about how the cosine function works, realizing that omega is 2 pi over t, and we got omega squared here. So now what I'm going to do is just solve for t, and there I have it, the period of oscillation of the charge as the system cycling through its oscillations. So I'll create a pause, allow you to copy this down. Again, it's not everything. It's just the highlights of the solution in case you might have to do it on the AP. So go ahead and jot that down. All right, let's move on we could graph this charge, and we'd oscillate between Q0 minus Q0, and it's a cosine function. We could calculate the period from this expression and actually put a number of seconds here and complete the graph. So we have the charge, the x-axis. We could graph it completely and accurately. We could also take the negative derivative of this, and the derivative of cosine is negative sine. The negative of that is sine. So the current goes as a sine function, and it would go like this, oscillating one sine function every time we go through a cycle. So we could graph also. So how do we compare, how do we find this current here? One way is we could take this expression, figure out what omega is, take the derivative, and then the term in front of the sine function would be Imax. But the other way to do it is to use energy conservation. For these oscillations, just like in a mechanical system with a spring, when a car is oscillating back and forth, in the end over here, we have no velocity, all spring energy, U spring. In the middle, we've got no spring energy. We have all kinetic energy. So the U spring equals kinetic energy. And somewhere in between, we've got a combination of the two. The same thing here. In the beginning, we've got only capacitor energy, U capacitor max. At this moment in time, when the charge is 0, we only have inductor energy, UL max. But somewhere in between, a moment in between here, where we got a little bit of charge, a little bit of current combined, we have both energies together. We could fill in the pieces by writing the energy of a capacitor is 1/2 Q squared over C. The energy of an inductor is 1/2 Li squared. And of course, in between, this is some intermediate charge less than the original. This is the current less than the maximum. We've got a combination of the two energies. I'm not going to do an example with numbers. What you would basically do is use two out of three of these and solve for one unknown variable. Like for example, maybe the problem tells you the original charge, the capacitance and the inductance, and they say, what's the maximum current that's going to be in the inductor? And you could just solve for I with a little algebra. Not that difficult. So it turns out that this calculation, according to the College Board's published curriculum, is the only thing in this topic that's actually supposed to be on the test. And knowing the concepts of why the oscillations happen, you have to write a short response or something like that. But this technically is the only calculation. But the AP has known to throw little curveballs, put things in the test that are not technically in the curriculum, so you have extra information just in case. So again, recap. The recap is that inductors are like inertia. They either fight the current as it's rising, or they fight it from falling. They try and keep the current constant. You could change it, but it's like, it keeps, it's like an effect that opposes that any kind of change. In a capacitor, that when the capacitor discharges, then it drives it to charge the other way. And then when it discharges again, now that it's going to drive it to charge the other way, and it just keeps driving that oscillation because it's like inertia in an oscillating system. Then possible differential equations, but focus in on your studies, I would say, with this energy analysis here. I think that's going to be the emphasis on the AP if this comes up. All right, I hope you enjoyed the video. I hope you found the physics interesting, informative, and I'll see you in the next video.